topics that you've heard about before and we'll hear about the rest of the afternoon. This is a really, really deep and rich topic that I possibly hope to cover all of it in 20 minutes. But there's one key thing that I actually want to emphasize, which is why do we care so much about power laws? Besides there being some fundamental aspect of human nature that is the desire to draw straight lines through stuff. So the big takeaway I hope to convey to you is why you see experimentalists and observers and theorists always talking about power laws in the context of turbulence. So the first thing I guess I want to emphasize is what is turbulence? There's a technical definition, which is a chaotic flow regime characterized by diffusivity, rotationality, and dissipation. That's a lot of words. So let's just say that turbulent fluctuations cascade from large scales to small scales where they are ultimately dissipated by some mechanism. Now the exact dissipation mechanism or mechanisms in a plasma is actually an open question in the focus of a session here at Sean. So I'll talk more about the turbulence dissipation challenge later. Why do we care so much about turbulence though? Well, as you heard in Francesco's talk, the corona is hotter than the photosphere. And the solar wind is actually much harder than we expect as well if we were just following adiabatic expansion. Now this dissipation that I mentioned earlier can actually lead to the heating of the plasma. If you have some large scales cascading down to small scales, eventually these small scales can get wiped out by collisions and that leads to irreversible heating. So turbulence can be a partial or possible answer to some of these big questions in solar physics. What does turbulence look like? Well, okay, here's the power law. This is turbulence. And it's probably not as exciting when you're looking at just something like this, so maybe there's a better picture we can see. So what I have here is a movie, which is a 3D reconnection simulation done by Bill Dotton and company with BPIC. This is a relativistic reconnection simulation, and you can see everything we just mentioned. You can see diffusivity, you can see rotationality in this turbulent flux rope that forms. And you may even believe that there's actually dissipation going on here. You can see these small-scale structures. I'll play it again just because it's such a gorgeous movie.
What are the colors represent? What are the colors?
So this is the out-of-plane current, the current out of plane with respect to the magnetic field. So you're looking at this and you're thinking, wow, this is very pretty, but it's a mess. And you don't really know if you can say much about it. But as it turns out, with the help of power laws, we actually can say some very interesting things about it. This is a relativistic reconnection simulation, and one of the things they cared about was how many particles in this reconnection simulation actually get up to relativistic energies. And it seems to follow a power law. So we're not just drawing straight lines because it makes us happy, we're drawing straight lines because it actually allows us to characterize what is a complete mess. A gorgeous mess, but still a mess. So you're probably thinking at this point, all right, now I want to start drawing some straight lines. So let's relate it to something that you've probably seen before, which is the Navier-Stokes equations. This is for neutral fluids. And what actually governs the turbulence in this case is this nonlinear term here, u dot grad u. If you start with some large eddy, this eddy breaks up into smaller eddies and continually breaks up until it reaches a small enough scale that it gets wiped out by viscosity. So what I want to do here is actually derive one of the important historical results in turbulence, which is Kolmogorov's 5/3 law, which allows you to say something about how energy is cascaded in neutral fluid turbulence. So let's make some assumptions about the turbulence. Let's say that the physics is universal. Okay, the nature of the turbulence does not depend on either how we're stirring the fluid or how it's dissipated. We're also going to assume that the turbulence is homogeneous. There are no special points in our turbulent bed. And that it's isotropic. There are no special directions. We're also going to assume the turbulence is scale invariant. More on this assumption later, especially when we come to plasmas. But we're basically saying there are no special scales. One large eddy breaks up into 2 eddies, which breaks up into 4 eddies, etc. And then we're going to assume that local interactions dominate. Now, if we assume these things, at every single scale, we have an energy injection rate, epsilon. And we can say that that energy injection rate goes like the characteristic velocity, delta U L squared, over some time scale, which we're calling the eddy turnover time. Now, as it turns out, we're dealing with incompressible MHD, so we've ordered out the sound speed, and the only time scale we can construct with dimensional arguments is the scale length L over the characteristic velocity function. And now we can relate our energy to the energy spectrum in K-space. We say that delta UL squared goes like the energy integral. This is one-dimensional, which we can do because we're assuming the turbulence is isotropic. And then with just some simple algebra, we can now say that the energy spectrum in K-space goes like the energy injection rate to the 2/3, K to the minus 5/3.
So I'm assuming E is going to be representing energy?
Yes, this is the energy spectrum.
Yeah. Not much.
So now you can pat yourself on the back. You've just derived one of the biggest historical results in turbulence. But we're plasma physicists. So what happens when we introduce a magnetic field? Okay, we don't deal with neutral fluids. We deal with magnetized physics. Can we derive a similar scaling law for how energy is cascaded in a magnetohydrodynamic fluid? So let's check our assumptions. Is the physics still universal? Well, we're going to say yes. This is actually an open question across all of turbulence theory, whether or not there is such a thing as universal turbulence. But there seems to be enough situations where you can say that the physics is universal that we're going to ignore. My understanding is that the physics where it's non-universal can be more of the exception and not the rule. Is the turbulence still homogeneous? Yes, there's still no special points in a plasma. Is the turbulence isotropic though? This is the big assumption that breaks down. Because now we have a magnetic field. And you might remember, using the Lorentz force, particles actually like to travel along magnetic field lines and not across them. So we can no longer assume isotropy. Is the physics still scale invariant though? We're going to say yes, but actually I kind of fibbed earlier, and this is technically not true either, for both neutral fluids and plasmas. All of the posters that came up earlier talking about intermittency, this is an example of how the turbulence is not necessarily scale invariant. You can have special scales, and that's these so-called intermittent structures. We're going to assume that local interactions still dominate, but there's an additional complication. Okay, we can't just use dimensional arguments concerning neutral fluids that just to say our only time scale is the eddy turnover time, because now we have the Alfvén time. We have the time at which electromagnetic information propagates in plasma. So how do we make sense of a system where we have two time scales and isotropy is no longer a valid assumption? So let's start with incompressible MHD. We have our momentum equation. Now our pressure has the magnetic component, and we have magnetic tension. We also have Faraday's law. And now we have resistivity as well. So our small scale is not just viscosity, there's also resistivity. Now I want to cast these equations in a different form, so I'm going to separate my magnetic field into a guide field portion and a fluctuating part. And I'm going to rewrite them in the Alsacer formulation, which is basically just obtained by adding and subtracting Faraday's law. Just some definitions. This B is again a guide field component plus a fluctuating component. We'll take the guide field to just be in the Z direction in this case. And our Z plus minus is our velocity plus or minus the fluctuating component of the magnetic field over the square root of 4 pi rho. So some notes about the Alsacer formulation. Here it is again. These are exact solutions to the Alsacer formulation. What do they mean? Well, they're just waves propagating up and down the magnetic field. One other thing I want to emphasize here is that we now have both a linear term and a nonlinear term. And furthermore, you might notice from this being Z to the Z minus plus and Z plus minus that our nonlinearity requires oppositely propagating Alfvén. And it's not just that they're oppositely propagating. They have to have non-zero relative polarization. What do I mean by that? Well, let's just Fourier transform the nonlinear part. And if we consider an Alfvénic fluctuation, whose polarization is the guide field direction crossed with K, our nonlinear component after being Fourier transformed looks something like this. This here, using identities for the scalar triple product, can be rewritten as Z dot K cross K. Our nonlinearity is K cross K. What does that mean? Here's a schematic. it means that alphanic turbulence is really a three-dimensional phenomenon. And this gets into issues that you'll hear about later this week of people arguing what kind of simulations you have to do. And arguing about exactly what we can ascertain from 2D simulations, because 2D are cheaper. But I want to emphasize that because the nonlinearity is k cross k, alphanic turbulence really is a three-dimensional phenomenon. Okay, so I've set up the Alsacer formulation. Now let's see if we can actually get some sort of scaling law. So I'm going to talk a little bit about one of the big advances in MHD turbulence, which is called critical balance. I'm going to define what's called the nonlinearity parameter, which is the ratio of the nonlinear term to the linear term. And with some scaling arguments, I can say that this goes like z k perp over v alphane k parallel. And furthermore, that z plus minus goes like the characteristic velocity fluctuation at a particular scale, k perp, over the alphane speed k parallel, which is actually the ratio of the alphane time to the eddy turnover time. Now, I want to argue that this parameter will naturally tend to order 1. So consider if the nonlinearity parameter is much less than 1. What does that mean? Well, it means two alphane waves interacting with each other don't really change them that much. So if I look at energy conservation and momentum conservation and just consider the k parallel component, what happens is that we can see that k parallel, one of the k parallels, has to be 0. And what does that mean? That means that there is no parallel cascade if my nonlinearity parameter is much less than 1. But if there's no parallel cascade, if the parallel component of my nonlinear interactions just sits at the injection scale, then my nonlinearity parameter actually has a dependence on k perp, or 1 over the perpendicular length scale you're considering. And that means chi grows as you go to smaller scales. This is, if you've ever heard in the context of MHD turbulence of weak turbulence becoming strong turbulence, this is what I'm referring to. I'm saying that even if chi, my nonlinearity parameter, starts very small, it will eventually grow to be order 1. What about the opposite situation? What if chi starts much greater than 1? Well, recall that the time scale at which electromagnetic information propagates in a plasma is the alphane time. So if chi equal to the alphane time over the eddy turnover time is much greater than 1, then the eddies in your plasma are uncorrelated. Can eddies remain uncorrelated? Well, that's kind of up in the air, but our standard picture of an eddy is a 2D structure. If you remember the movie where you had this long turbulent flux road, at each slice it was some sort of 2D structure, and these were all connected, they were all rotating together. So if our standard picture of an eddy is a 2D structure, but the only way fluctuations can remain 2D is if information can propagate, we can argue that uncorrelated eddies might cascade towards chi of order 1. Or another way you might think about this is if you're wiggling a magnetic field, your magnetic fluctuation will travel along the magnetic field line. And what that means is the way you wiggle it will be on some perpendicular length scale. And as that perpendicular length scale travels, the only way you can make sense of how far it travels is if your actual alphane time and your eddy turnover time are of the same order. So this is called critical balance. If I take the alphane time and the eddy turnover time to be the same order, we can now derive what's called the Goldreich and Schriehar scaling law for MHD turbulence. It goes very similarly to Kolmogorov's 5/3 law. I start with defining my energy injection rate to be some characteristic velocity fluctuation squared over some characteristic time scale. I'm going to take that to be the eddy turnover time, which depends on L perp. And with some algebra, the same algebra as before, I get the same scaling law, but it's not k anymore. It's the perpendicular k. And if I consider critical balance, that the alphane time and the eddy turnover time are the same order, I can now see that there's a weakened parallel cascade. In fact, in MHD turbulence, the wave vector anisotropy grows with increasing K-per. And I want to emphasize this because of a plenary talk that will happen later in this week by Bill Dorland, which will talk about the application of a particular reduced model for kinetics called gyrokinetics to plasmas. If your wave vector anisotropy is growing with increased K-per, you can actually possibly apply gyrokinetics because gyrokinetics works in the machine where anisotropic fluctuations rule, where K-perp over K-parallel is much, much greater than 1. And you can also derive a parallel cascade. So I've done some math, and you maybe don't believe this. So let's actually show some observational evidence for this. This is from Olga Alexandrova looking at Ulysses data. This is the magnetic energy spectrum versus frequency. Higher frequencies correspond to higher K-perp. And this minus 1.7 is really close to minus 5/3. Minus 5/3 is minus 1.667. So there is some evidence to suggest that Goldreich tree harmonics grow. Now you'll also notice in this picture that there's what's called a spectral break at 1. What is going on here? Well, now you're at scales below the ion gyro radius. You might remember from any class in which you derived MHD that MHD takes the ion gyro radius to be 0. Doesn't exist. So if you actually do reach the scale at scales below the ion gyro radius, you're considering a situation where the ions have become demagnetized, and you can no longer consider the plasma as a fluid. Kinetic turbulence is more complicated, but it's also heavily related to a physical process we discussed earlier, and that's dissipation. There's a lot of things that can be going on at kinetic scales where kinetic turbulence matters. You have Landau damping, you have collisionless reconnection, you have possible cyclotron damping, and maybe this phenomenon called stochastic heating, which Ben Chandler will talk about later this week. So if you enjoyed this talk, I would highly encourage you to check out the following sessions, which are actually going to talk a lot more about kinetic turbulence, more than I could possibly hope to talk about in 20 minutes. Bill Matthews has a session on from fluid to kinetic scales. There is this turbulence dissipation challenge where people are going to argue about exactly what models capture what dissipation mechanisms. And then Greg Howes also has a session on distribution function dynamics and how they affect kinetic scales. So here are some references. These are detailed more on the website. I sent quite a lot, long paragraphs about what I thought about all of these references. One thing in particular I want to emphasize is this Matthews and Veli space science review. So this is not evolution versus creationism as far as teaching the controversy. There is actually still an open debate about Goldreich and Schriehheim and the importance of wave physics. So I really want to emphasize this particular reference if you're interested so that you can read it and form opinions of your own about exactly how MHD turbulence works. I can take any questions now.
I think so in one of the last slides you showed about experimental data.
Upstream, yeah.
Yeah. I didn't understand what is the evidence of critical balance in this.
This isn't evidence of critical balance. It's evidence that the spectrum matches K to the 5/3. So as far as if you're looking for observational evidence of critical balance, I would recommend talking to Alfred Mallet, who's been doing a lot of statistical analysis on whether or not critical balance is true from wind and Ulysses data. I think he actually might be giving a talk during the Bill Matthews session. But yeah, this is just that the spectra seems to suggest minus 5/3.
You show a spectrum from one simulation in your slide.
Yes.
Do you know where the particle, I mean, which portion of particle the statistic based on? It's only for the particle in the current heat region or in the whole domain?
I'm sorry?
I mean, because you need to do this kind of plot, people need to use a lot of particle.
Yeah.
I mean, do you know where the particle they take from? Only in the current heat region or in the whole simulation domain?
I'm pretty sure it's only in the current sheet region, but I'm not 100% on that.
No, I think it's probably cobalt
Oh, okay.
for all the particles.
Okay. Yeah. Yeah.
I just want to say that I think you did a really good job presenting something that's very complicated and hard for some people who don't focus on turbulence. So, I just want to say that you did awesome.
Yeah, thank you.